Albarqouni, who is a Palestinian-German professor of computational medical imaging research at the University of Bonn, and an AI Young Investigator group leader at Helmholtz AI. I think he will introduce himself more, so I'll hand over
just skip that slide.
Okay.
Sometimes, so that's absolutely fine. So hi everyone. Let me. This is Shadi Albarqouni, and you might wonder, well, why do you have just empty abstract on the website? Indeed, I get involved in teaching for the first time since 2 years. I had to teach for the semester, and I didn't have indeed much time to fill in the abstract in the Google form. Nevertheless, what I'll be talking about is indeed I'll be introducing the challenge of the computational imaging research from the clinical and from the technical perspective, before I briefly introduce the federated learning and probably show one of our use cases that has been just recently published at the Nature Machine Intelligence a few weeks ago. So before we start, may I ask you how many of you have, came across this book by James Stravinsky? Only a few, okay. So what James indeed was trying to make the case that a large group of people would indeed, like crowds, would be much smarter than individual, no matter how brilliant they are, yeah? And he brought a couple of real cases, real world examples, like from the CIA, etc., trying to say that, the crowds could be really better at making right decisions, even wiser decision, and also probably predicting the future. However, he set few conditions to utilize this collective intelligence. So I'm going to say these, I'm going to tell these conditions at the very end of my talk. But this is the most important slides, I presume. So let me move on now to the challenge in the clinical workflow. So this is mainly a radiological workflow. And indeed, what we do have, there's staff shortage, and also there's a heavy workload on our radiologists. Of course, that led to error and discrepancies that has been reported in the literature. And also, what probably makes things worse is this trend into observed variability among the physicians or radiologists. That, of course, brought a lot of challenge, the interesting challenge from the computational point of view. And this is indeed what shaped also our research portfolio. So we start thinking about, how we could train models from only a few annotated data. And of course, you could think about, self-supervised, semi-supervised, etc. But the more data that you bring into to the machine learning platform, then you would have these kind of domain shift discrepancies where you need really to attack with domain adaptation or image-to-image translation, right? And the more think you about generalization, not only to unseen domains, but to probably unseen classes. For example, here, the work that we did with Facebook AI research, how we could generalize the model to unseen organs, just like with the meta-learning or few-shot learning. But we are not dealing with also medical imaging. There are also like multimodal data, which is like, I think Holger mentioned that earlier. We do have electronic health records or some meta information that we need also to integrate into our predictive models. And this is where I investigated a couple of works of geometric learning or GCN graph convolution networks, etc. So this is like, of course, you keep doing so until you reach whatever average performance or the desired performance that you're interested in. But then we come to another layer of complexity where we would like to understand, the quality assurance, right? This is something, the tools that we need to provide. And this is where we touch upon the topics of robust optimization, quantifying the uncertainty, and probably, do out of distribution detection to tell if these data points comes from the same domain or another one. And of course, fair representation. But then I realized that indeed, what we probably need is more how we could aggregate the data. And the more data that you bring into the models, well, the better the performance, right? And that comes at no surprise. I just want to skip this slide. I think we have seen this many times. But that comes at no surprise, as we have seen a couple of works in the literature showing the more data or access to a larger scale database is indeed the key to improve the performance. However, this is not straightforward, in particular in the medical domain, as we saw a couple of examples where, well, the data was compromised, right? Or the identity or the privacy was compromised when you do have access, like, for example, to CT data and to some face recognition databases, right? And this is where, like, a couple of regulations just came out, and there's a lot of recommendation where, well, collaborative learning, federated learning, privacy preserving, machine learning would be probably the keywords in the next few years. That brings me indeed to one of the questions that I tend to ask in my talks. What are the main challenges that you do foresee in federated learning? There's a slider that, of course, you could probably, well, vote there, but I'm not really expecting you to do so. The reason is just of interest of time. I would probably skip this slide and just show you a couple of results that I had previously. So this is one of the results that I get. It's like just a little, like 14 participants who get access to a slider and just vote. And the majority were telling, well, standardization is one of the big challenges, yeah? And you could probably see, well, the standardization, like image annotation, labeling, I think Marco mentioned also the convention, naming convention, etc. This is one of the challenges that we might have. And there must be some sort of intersection with the data heterogeneity as well. So let's have another example. Another 14 participants, but well, they were telling like 57%, they were saying data heterogeneity would be one of the challenges or major challenges, followed by the privacy issues. Another sample, probably bigger one. Again, they were telling the data heterogeneity is one of the major challenges in federated learning, and in particular in healthcare. So when we talk about data heterogeneity, well, there are tons of cool stuff here, mentioned population, class imbalance, bias, domain shift, etc. And this is not surprising, right? I mean, we have seen also a couple of works showing how indeed, well, the performance of these federated learning just drastically drop up to 50% whenever you do have non-IDs, right? And of course, there are tons of solutions to mitigate these problems. So I'm not going through these solutions at the moment, but I want to indeed just talk about why this data heterogeneity is one of the biggest problems, at least in the healthcare domain. Well, it turns out it has a couple of like factors. One of them is the inter and inter-scan variability. I mean, we're going to see also this example in our use case. Another factor is indeed the demography, the population, right? We do have multimodal data. And there must be some also noise in both like the measurements X and also worldwide, the annotations, the labeling, etc. So all these contribute to data heterogeneity in the medical domain. So what I'll be showing you next is indeed one of the examples that we were trying to work on for, oh yeah, this must be also has been shown today by Marcos, how we could, well, how federated average simply doesn't work, or, well, it's just performed probably worse than even individual clients, right? In particular, if you do have heterogeneous data. So what I'll be showing you next, and this is like the second part of the talk, is our use case on brain tumor segmentation, but in unsupervised fashion. And that was built on top of like previous works that we did in the past to do brain tumor segmentation. Again, in a supervised fashion. So the idea here is we need to train, well, the P of X. So we need to model the probability of your data, given tons of distributions coming, well, across different sites, right? And you might wonder why you need to do so, why we need to model like healthy brain data, for example. Well, it turns out that if you model the healthy data and how they look like, well, you could easily spot whatever like hyperintensity or anomalies in the brain imaging. And this is what we're going to see later that we were able to generalize this model pretty well on 6 different sites that have never been seen during the training. Okay. So let me give you a little bit background, as I say, because that was built on previous work. So basically what we were doing here, we do have an autoencoder, convolutional autoencoder. Well, we train these autoencoders on healthy brain MR data. And you could use whatever loss function, like whatever, L2, adversarial loss, perceptual loss, whatever loss function that you do have. And during the inference, there's a greenish part here. You pass in you feed in like with the anomaly data, like a brain image with some anomalies. And what you would probably get, or ideally get, a pseudo-healthy version of that brain image, right? So whenever you do the residual, hopefully you get the anomalies or the lesions. It turns out that it works pretty well in practice, well, to some extent. So you can see here on the bottom line that these anomalies, these are the residual that you get from the convolutional encoders, which match pretty well the annotations on the second line, second row, that were annotated by our radiologist. Quantitatively, you can see here that the unsupervised models performs or outperform the simple thresholding that we see, that we get from our radiologists from the clinical DSR. But what was surprising to me, that these unsupervised models generalize much better than a supervised model if you use this transfer learning. And this is where we thought about, well, let's scale this up and let's see if we get, because that was used on single database coming from our partner. Well, what about scaling this up to, well, use publicly available databases and see how that works on federated fashion. Again, we use 0 annotation. So there is well, we are not asking for much more from our radiologists, only the data that they do have. So, however, one of the challenges that we expect to see is, again, the data heterogeneity, all this inter and intra-scanner variability. I'm going to show you this example that came from our partners at the clinical DSR at Munich. So what they show here that the patient, the same patient, has been scanned a couple of times, different data points from different scanners, Siemens, Philips, GE. And what our radiologists were trying to do, well, trying to do this whatever simple thresholding approach to quantify the lesions, right? Which is quite important for whatever treatment, monitoring, etc. And what you're going to see here on the right-hand side is indeed the volume of these lesions. And you could see here, for example, if the patient has been scanned on October 7th by a Siemens scanner, the volume would be like 5 milliliter. But if he gets scanned like 3 days later by another scanner, let's say GE, then the volume of the lesions would be just double, right? So this is quite critical. And this is what we thought about, well, bringing these databases from different sites with different scanners might be really crucial. And we really need to find probably innovative solution. And we saw that already, like with the benchmark that Mark was just from Flampe, where, well, the federated average simply doesn't work with this heterogeneous data. So what we were trying to do, well, we thought, well, the brain data, in part, like lucky we are, like we work with brain data, which is like more rigid organ. So we thought this is like in most of those sites, since we work with healthy data, would be sharing the same anatomical structure, right? So, and of course, like this would be quite different from one site to another, according or depending on the site that or the scanner that they might have. So we thought, what about disentangling the latent representation to one capture this shape, which is the anatomical structure, and another one to capture the appearance. Yeah. So you could think about, yeah, the appearance would be just styling this kind of shape representation. And to enforce this, we introduce a loss function in addition to whatever perceptual or L1 loss. So the first one we call it shape consistency loss. We were indeed like trying to, well, manipulate the image different appearance and see if we could just bring the two representations close to each other. And the other loss, we call it latent orthogonal loss, where we're trying to push the shape and appearance apart from each other. So we don't want to have these, well, latent representations share the same thing. So we trained the model on 3 publicly available databases, like with 1,500 scans and 3D scans. And we did test it on 6 different pathological databases that have never been seen before. That contains a couple of pathologies like multiple sclerosis, glioma, glioblastoma, etc. And let me show you probably some qualitative results. Oh yeah. So the first thing I want to just show you here, this is the latent space of our representations. And you can see here like 4 examples of brain image with different appearance. Well, they share the same anatomical structure, right? And you can see how they are embedded close to each other in this kind of, shape representation. However, their appearance are, well, sparsely embedded in the latent space and probably clustered in different clusters or groups. And maybe I could show you probably one more slide here, where we show indeed how our model was doing much better job from like other local models and even the federated average in detecting the brain lesions. And of course, there must be some, well, as you can see probably in the figure on the left-hand side, bottom left-hand side, well, the models, most of the models indeed didn't perform well for small lesions, which are, well, I think some of them are clinically insignificant. But I think this figure suggests that there's a lot of work to do to improve this. There are a couple of figures that I would probably skip here, that we were just doing some analysis across gender, age groups, just to see if there is any bias was there. But a lot of work we have been doing, indeed, there is also some works. I heard really interesting stuff from also Nika yesterday about the interactions between the clients and peers, etc. And this is where we introduce like this kind of mixture of experts and peer coaching or peer learning between also the clients, so they could talk to each other and probably learn from each other some experience. And this is where we indeed published also at Melba and was presented in MBZUAI last year. And another work, recent work, where we, well, and of course, the second work with the skin lesions, we also assume that, well, there's some clients, they have 0 annotations. A couple of them has partially annotated data, etc. So that was in semi-supervised fashion. The last example, you see liver segmentation. This is where you assume that the model or the clients have MR, CT, different modalities or mixture modalities, MR and CT, and the task was to do liver segmentation across different modalities. And it turned out, well, we just used simple or like a simple normalization technique called mode normalization, and worked pretty well for both modalities. But nevertheless, there are tons of works that needs to be done though. Like, I think it has been discussed already. Privacy preserving, security, interoperability, generalization, incentives and fairness. And I very much like also the federated learning in low resource settings. So to probably finish with the slides, and this must indeed conclude the presentation. Well, the conditions that James indeed were setting for utilizing this collective intelligence. The first one, and this would probably address what Marcus' question about how we could indeed build these kind of federated learning models. First is diversity. And you could, of course, draw the analogy here. You really need to have, I mean, we should really use these clients, no matter how diverse their data or whatever data, cohort selections, etc. I think we need really to make use of these data. They should be independent. So every single client should come with their independent thoughts, knowledge. And I think the third really condition is quite important. the decentralization. So every client or subset of these clients has their tech knowledge, yeah? I mean, you know, this kind of environment, culture, this is like in reality, right? When we talk about like clients, there is this kind of, you know, local knowledge. So you need really to give them some space to work on their data. I think we have seen also a couple of works where they show these adaptation steps that might be needed, right, to make it work. However, the most important condition is the coordination and aggregation. So without proper coordination and aggregation, I think all these kind of stuff wouldn't matter. So I think that concludes my presentation. I think there are a few only remarks that I would like just to raise. So apart from like the community service, where we, together with Holger, that we are having this special issue at TMI on federated learning. We're also organizing a workshop on distributed collaborative federated learning. Last time was in Singapore. But what I'm highly interested in, indeed, the other workshop also called Federated, it's called Affordable AI in Healthcare, where we are really interested in, AI development in low resource settings. And in particular, those applications that are coming from low middle income countries. Also, like I'm a member of this Arab German Young Academy, where we also bring a couple of like, have initiated a lot of projects where we'll level up like the skills of the graduates, and also like raise a couple of like awareness campaign, like for example, we see here in Tunisia, Egypt, and Palestine. I think that's it. There are also like a few openings for I think the students who are listening to us. One of them is quite interesting, and probably it goes in line with Anne said, is that affordable federated learning, where I'm highly interested in indeed federated learning with low resource settings. Thanks a lot for listening. Happy to take questions.